Numbers. We use them all the time, but what are they? Why do they behave the way they do? Why is -1 times -1 equal to +1? And is it really true that 0.999 recurring is the same thing as 1? Does it make any sense to multiply together √2 and pi? 0.001 recurring is a rational number. And if we square it, what's the answer? Numbers are used for all sorts of different jobs, and different jobs need different sorts of numbers. To do analysis, we need the real numbers. And in this program, we're going to see exactly what the real numbers are and how you manipulate them. But let's start by looking at some of the properties of the simplest kinds of numbers, the integers. Well, positive integers, the natural numbers, have been around since man first started counting. For example, these are tally sticks. They were used for centuries for counting and recording. Each of these notches corresponds to one item, like a sheep. At the end of a commercial transaction, the stick would be split in half. Each half then acted both as a receipt and as a record of what had occurred. Adding natural numbers is a simple idea. 2 notches plus 5 notches makes 7 notches. And subtraction is the reverse. Start with 7, take away 2, and you get 5. Multiplication is also a simple idea. 2 lots of 5 makes 10. Well, now let's look at a job where we need negative integers and 0, measuring temperatures. For instance, 0 degrees Celsius is the melting point of ice. So we have to have negative numbers to describe temperatures less than that. It makes sense to talk of a temperature of -40, for example. Well, adding and subtracting integers is straightforward, but multiplying them is not so simple. Saying that -1 times -1 is equal to +1 seems a bit mysterious, but it isn't really. It comes from the distributive law. Let's see how that works. 7 is just 3 plus 4. So 2 times 7 is 2 times 3 plus 4. Splitting up 7, that's the same as 2 times 3 plus 2 times 4. And in general, given any positive integers, a, b, and c, a times b plus c is the same as a times b plus a times c. Suppose we want this to hold for all integers, positive and negative. Here's the distributive law. If we substitute -1 for a, 1 for b, and -1 for c, and then apply the law, we get this. Now the left-hand side is just 0. And the right-hand side is -1 plus -1 times -1. Adding 1 to both sides gives 1 equal to -1 times -1. So, if the distributive law is to hold for all integers, the last line must be true. But in the real world, we wouldn't get far with just the integers. Suppose I cut this cake into equal pieces. If I want a number to describe this piece, then the number system has to be extended to include fractions. And like the integers, fractions can be combined in a natural way. If the cake is split into 3 equal parts, each one is a third. That is, 3 times a third equals 1. Combine 2 of these thirds, and we get 2/3. Adding together 1/3 of the cake and half the cake, we get 5/6. And half of a third is just a sixth. So, the rules of arithmetic for integers do still work for fractions. Dividing up this cake gave us an idea of fractions. That is, of rational numbers. But how can we picture all the rationals? Well, one way is to use a number line.
This number line shows some of the integers. Here's -1, 0, 1, 2, and so on. Let's add some rationals. Here's 3/2 and 7/8. And here's some more. 1/2 and a third. Of course, we couldn't mark all the rationals because there are just too many of them. In fact, given any two rationals, we can always find another in between them. For example, the point midway between a half and 7/8 is also rational, and so is the point midway between that and 7/8. And although we can't mark all the rationals, it is possible to order them. That means that given any two rationals, we can always find which is the greater. For instance, 19/22 is about here, just to the left of 7/8. But why to the left? Well, we can easily decide the order using equivalent inequalities. Let's write 19/22 and 7/8 over the common denominator, 88. And now it's clear the inequality goes this way round, because 76 is less than 77. So 19/22 is less than 7/8.
But there's another way of representing the rationals, as decimals. Here are some of the rationals we've discussed so far. Now, both a half and 7/8 can be represented by terminating decimals. You can get these decimals by long division. However, if you try long division with a third, or 19/22, you don't get decimals that terminate. Instead, you get decimals that are recurring. 1/3 gives 0.333 recurring, and for 19/22, it's this 6/3, which keeps repeating. And from their decimal expansion, you can see straight away which is the larger of two rationals. The 7 here is greater than the 6 here, and that means 7/8 is greater than 19/22. So we could use the decimal expansion of the rationals to order them. In fact, these two sorts of decimal are the only ones you can get for rationals. They're all either terminating or recurring. We could even think of these as recurring. It's just that the recurring digit is 0, and so we don't usually bother to write it. Now, each of these expansions corresponds to a unique rational. It's obvious what it is for these two, and given any recurring decimal like this, we can work out the corresponding rational by using a simple algorithm that you've met in the unit. But there's another way of thinking of recurring decimals. This is 3/10 plus 3/10 squared plus 3/10 cubed, and so on. In other words, as an infinite series. Well, you'll meet infinite series in a later unit. Now, all these decimals arose by long division. But there's one kind of recurring decimal which doesn't arise from any rational by long division. One like this, which ends in recurring 9s. Numbers like this do keep cropping up, so what do we do with them? Well, what we do is to define this as an alternative representation for 1. Intuitively, this may seem all wrong. It looks as if this has to be just a little less than 1. But as you'll see later in the program, if we stick with this definition, it is consistent with the rules of arithmetic. In fact, if we don't define it this way, arithmetic goes wrong. Before we do that, though, let's look again at a third. What does this decimal representation tell us about where a third is on the number line?
Well, here's a third with its decimal expansion. Now, this is really a neat way of expressing a whole sequence of inequalities about a third. You can clearly see that a third lies between 0 and 1. That is, a third has decimal point something. And if you look more closely, you can see that a third lies between 0.3 and 0.4. Its decimal expansion begins 0.3. Now, to get more information about where a third lies, we use the next decimal place. That tells us that a third lies between 0.33 and 0.34. And if we repeat this, we can see that a third lies between 0.333 and 0.334. Each of these inequalities arises from the decimal for a third. The numbers on the left, 0, 0.3, 0.33, 0.333, and so on are all less than a third, but they form an increasing sequence which tends to a third. And the ones on the right form a decreasing sequence which also tends to a third. We'll be discussing sequences and their limits in the next unit. Now, so far, we've looked at the integers and the rationals, and we've seen that they can all be represented as decimals. But it turns out that there are lots of magnitudes, in geometry, for example, which can't be measured by rationals alone. So let's look at one example. Here's a square of side 1. What's the length of its diagonal? Well, let's measure it. It looks as if it's a bit more than 1.4. But how big is it exactly? Well, according to Pythagoras' theorem, it's root 2. That is, it's a number whose square is equal to 2. However, it turns out that there is no rational number whose square is 2. There are several ways to prove this. There's an algebraic one in the unit, but here's a geometric one. It's a proof by contradiction. We start with a square of side 1. Let's assume that the diagonal can be written as a rational m over n. If we scale this up by a factor n, it's the same as saying that a square with side n has a diagonal of length m, where both m and n are integers. Now, because m is bigger than n, we can mark off a length n on the diagonal. That is, the diagonal has been split into two integer lengths, n and m minus n, and it's the top bit we're interested in. M minus n is an integer, so to make life easier, let's call it k. We can construct another, smaller square with integer side k. And it turns out that the diagonal of this square is also an integer. Now, why is that? Well, if we draw in this line, we get two congruent triangles. So this length and this are the same, that is, k. So the new diagonal has length n minus k. Let's call it L. So, by starting from a square with integer side n and integer diagonal m, we can construct another square with integer side and integer diagonal. The only difference is in the sizes of the two squares. The second one is smaller than the first. Now we can repeat this process as many times as we like. The squares get smaller each time, but we always have integer lengths for both side and diagonal. But that's not possible. Because the lengths get smaller each time, eventually the side of the square has to be length less than 1. So we've reached a contradiction. So a square with integer sides and diagonal is impossible, which means this isn't possible either. A square of side 1 can't have a diagonal which is of a rational length. So how do we describe the length of the diagonal?
Well, the only thing to do is to introduce a new sort of number, which we call root 2, and which we can use in arithmetic in the same way as rationals, except that whenever we get root 2 squared, we replace it by 2. And in the same kind of way, we can introduce numbers like root 3, root 5, the cube root of 7, and so on. None of these numbers can be rational. They're called irrational numbers. And we can do arithmetic with them with a bit of care. For instance, we say that root 2 times root 3 is equal to root 6. That fits in with the laws of arithmetic. But how big are these irrationals? For example, where does root 2 lie on our number line? Is it possible to represent root 2 by a decimal, as we did with a third? We know root 2 lies between 1 and 2, because 2 lies between 1 and 2 squared, and that it lies between 1.4 and 1.5, because 1.4 squared is less than 2, whereas 1.5 squared is greater than 2. And if we check the squares of 1.41 and 1.42, we see that root 2 lies between 1.41 and 1.42. And by continuing this process, we get a sequence of inequalities which give more and more accurate decimal approximations to root 2. And we represent this infinite process by writing root 2 equals 1.414 and so on. But because root 2 is not rational, this decimal expansion won't terminate or recur. But in analysis, we need numbers to describe many other things. For example, if this disk has radius 1, what's its area? Well, we usually describe its area using the number we call pi. But we also need numbers to describe zeros of polynomials, like this one. It's x to the fifth plus x minus 1. Its graph appears to cross the x-axis here at a. But is there really a number a such that a to the fifth plus a minus 1 is equal to 0? Well, if there is one, then it will have to be like this. Because if we put 0.7 into this formula, we get a negative answer, whereas 0.8 gives a positive one. With 0.75, it's negative. With 0.76, it's positive. So a must lie somewhere between 0.75 and 0.76. If we carried on like this, we'd get a better and better idea where a must be. Well, of course, we'd certainly expect any function which has a continuous graph, like this one which goes from negative to positive to be 0 somewhere. So we certainly want numbers like this one to be in our number system. Well, what about pi? As you'll see in the next program, we can represent this area by an infinite decimal too. Here it is. Both these numbers turn out to be irrational, and so their decimal expansions will have to be non-recurring.
So we now say that any decimal, whether recurring or not, is a real number. And because we know how to order decimals, we can order our number line. For example, here's a, and root 2, and pi. The set of all decimals is the set of real numbers, r. Well, it's all very well to say that every infinite decimal represents a real number, but can we do arithmetic with infinite decimals? For instance, how can we work out the product of root 2 and pi from their decimals? We can make a start by truncating the expansions and working out that product. So 1 times 3 gives 3. The next product is 1.4 times 3.1, which is 4.34, and so on. These look like better and better approximations to the product. But how can we be sure? And what exactly do we mean by the product? Well, we can define it using the idea of a least upper bound. Suppose these dots and intervals correspond to a subset E of R. If all the points of E lie to the left of a particular number, say 4, that is, every number in E is less than or equal to 4, E is said to be bounded above by 4. Any bigger number, 5 say, is also an upper bound. But here it looks as if there are some numbers smaller than 4 which are also upper bounds. What is the smallest or least upper bound of E? Indeed, does E have a least upper bound? Well, what do we mean by least upper bound anyway? M is said to be the least upper bound of E if, firstly, M is an upper bound of E, and secondly, any number less than M is not an upper bound of E. But what if we know nothing about a set except that it's bounded above? Must it automatically have a least upper bound? Well, it does. Every set E that's bounded above has a least upper bound. This is an important property of the real numbers called the least upper bound property. The least upper bound is also called the supremum of E, written as sup E. This is very reassuring. We may not always be able to find the least upper bound of a set precisely, but at least we know that there is one. Now, we wanted to be able to define the product of root 2 and pi. And by truncating these decimals, we got this sequence of approximations to the product. So a natural way to define root 2 times pi is as the least upper bound of this set of numbers. But does it have a least upper bound? Well, each truncation for root 2 is less than 2, and each for pi is less than 4. So the product is less than 8. So the set of products on the right is bounded above by 8. And so, by the least upper bound property, this set does have a least upper bound. We can use this least upper bound to define the product root 2 times pi. And that means that we've answered another of the questions we posed at the start of the program. We've used the least upper bound property to define the product of root 2 and pi. And we can use the same idea to multiply any two real numbers. So what would happen if we multiply 3 by a third using this method? So the sequence of products is this: 0.9, 0.99, 0.999, and so on. So the product of 3 with a third, using this method of multiplying, is the least upper bound of all these numbers, 0.999 recurring. But of course, 3 times a third is 1. So for consistency, 0.999 recurring has to be 1 as well, as we said earlier. In fact, we can define sum, difference, and quotient of any two real numbers in the same kind of way. And all the normal rules of arithmetic still apply.
At the start of this program, we posed these questions. Why do we say -1 times -1 equals 1? Well, we answered that by showing it had to be true to make the distributive law work. And why is 0.999 recurring equal to 1? Well, I hope that by now we've convinced you that that has to be true too. For one thing, it fits in with the least upper bound property. And we showed that we can use that property to define the product of root 2 and pi. Here it is given to 6 decimal places. Which leaves just one question. What is 0.001 recurring all squared? Well, we could apply the least upper bound property again. Truncate the expansion, work out all the products, and take the least upper bound. But remember, this is a recurring decimal. So we could convert it to a rational, square that, and then convert it back again to a decimal. And we know that decimal expansion must be recurring. But how long is its recurring block? Well, here it is. It's 2,997 digits long.